Slips, slippery liquid-infused porous surfaces. The slips technology is inspired by the insect trapping mechanism of the Nepenthes pitcher plant, a carnivorous plant found predominantly in the Old World tropics. When dry, insects have no problem traversing the upper part of the pitcher called a peristome. However, when a coating of water is applied to the rim of the plant, the unique surface traps the water and creates a slippery surface which insects cannot hold on to. They plunge into the pitcher, are trapped in the viscous fluid, and are digested as food. Inspired by the natural mechanism, slips was developed by first creating a functionalized porous structured solid and then infusing a suitable lubricating fluid into the solid. This combined system can repel many immiscible fluids. Slips not only mimics what nature does, as in this example of an ant sliding down the front of a slip surface, but it can also do what nature cannot. Slips can even repel complex fluids such as crude oil. Here we have a piece of aluminum with 3 different surface treatments, with slips at the top, super hydrophobic in the middle, and hydrophobic at the bottom. As the crude oil is applied from the top, it slides on the slip's surface, leaving no residue. The middle and bottom surfaces cannot repel the oil and are both stained. Even at very high temperatures, the repellent property of slips is still highly effective. At 200 degrees Celsius, when crude oil is applied to the super hydrophobic surface on the left, it quickly sticks and begins to smoke. However, when applied to the slip surface, the oil easily slides off. Slips also shows excellent damage tolerance and self-healing characteristics. A razor was used to demonstrate mechanical damage by scoring and scratching the slip surface. The slip surface quickly self-heals and the damaged area does not lose its slippery characteristics. Slips shows excellent easy-to-clean properties. On a slip surface sprinkled with dust particles, a drop of liquid is applied. As the substrate is swiveled and the droplet slides around, the dust particles are picked up by the droplet, leaving the slip surface clean. Slips has unmatched anti-stick property. A strip of Scotch tape is applied to the slips treated circle on the left and a Teflon circle on the right, each placed on a table. When the tape is peeled from the slip circle side, it remains on the table. In contrast, the Teflon circle is picked up by the tape. Here, bacteria was cultured on a super hydrophobic surface and on a slip surface. After 24 hours, the puddle of bacteria is stuck to the super hydrophobic surface, indicating the bacteria has begun to form colonies on the surface. On the slip side, the bacteria were unable to attach to the surface and easily slide when the substrate is tilted. Slips is optically transparent and even anti-reflective. Motor oil is applied to an untreated lens on the left and a slips-treated polycarbonate lens on the right. The slight curvature of the lens is enough to make the motor oil slide off the slips-treated side, keeping the lens clean, even under apparent harsh conditions. With all of these properties, it is easy to envision the many applications of slips. Slips can be used to quickly and easily remove biofouling with a very low shear force, such as passing through an air-water interface. Algae was cultured on this glass slide. The right half was treated with slips. As the slide is removed from the water, the algae culture easily slides off the slips-treated surface. However, the algae growing on the non-treated surface is healthy and unharmed. And by the way, the release property of slips also highlights the opportunity to easily grow and then harvest cultured organisms. Similar to the previous example of motor oil on a polycarbonate lens, slips can also be used in non-fouling optics. In this example, liquid asphalt was used instead of motor oil. Slip surfaces are ice-phobic and effectively slow down ice nucleation. Condensed water droplets on a cold, slips-treated aluminum surface easily slide off before they have time to freeze. In this example, ice quickly forms and frost formation occurs over the entire surface of this untreated aluminum. On the slips-treated aluminum, there is almost no ice formed, and droplets continue to slide off the surface. There is a small amount of ice formation along the edges. However, it is clear the ice is growing from the surrounding untreated surfaces. This is the so-called edge effect. With continued cooling, both surfaces will eventually be covered with ice, but far less ice will be accumulated on the slips-treated surface. When it is time to remove ice or defrost a slips-treated surface, heating the surface just above the melting temperature is sufficient to remove all ice. No droplets will remain, effectively making the surface completely dry in a matter of seconds. Though ice also melts on the untreated aluminum, when heated above the melting temperature, there are still many droplets pinned on the surface. What would happen if you start to cool the surface again? The droplets will immediately freeze. In order to fully dry the untreated aluminum surface, it would need to be heated for a much longer period of time, thus wasting energy. If slips was applied on refrigerator coils and heat exchangers, for example, substantial energy savings could be realized.